All right, so today's lecture is going to be on the linear model and OLS in the cross-section. All right, so today's lecture is going to be the first part in a series of lectures covering various topics within the umbrella topic of linear panel data models. So while today's topic is not specifically on panel data, it will serve as a nice prelude to the following, well, almost handful of lectures. Just to remind you guys of our current setting, when we're talking about cross-section, or cross-sectional data, the structure looks something like this. We have observations, we have a collection of observations, usually subscripted by an I. The subscript itself doesn't really denote anything except identity, and the order doesn't really matter, but your data set may look something like this if you open it in its data or whatnot. There's a column dedicated to the outcome variable of interest, y, as well as several columns for the regressors, usually denoted by x. Note here that we use the superscript k to denote the coordinate of x, to denote a particular coordinate of x, and that we're treating x as a row vector following the notation in Wooldridge, as well as the Wooldridge book that you used in your previous econometrics course. All right. So in this course, we will assume throughout that we have access to independent and identically distributed observations, or IID data for short, which means that when we're talking about observations for different cross-sectional units, those observations are independent of each other and they are drawn from the same distribution. So we're talking about having IID data. Unlike your previous econometrics course, our focus here will be less on finite sample results, which are rarely available for the topics or estimators in this class. Instead, our focus will be on asymptotics, and specifically on asymptotics as the number of cross-section units. On the previous slide, that would be the capital N, as the number of cross-section units grows without bound, that is, goes to infinity. That means that whenever you see an arrow in this course, whenever you see a limit or an arrow of any sort in this course, it's understood as being some sort of convergence as n goes to infinity. Now, our interest is not in the asymptotics per se, but rather we'll use asymptotics as a vehicle for constructing good approximations. Now, implicit in our focus on asymptotic, implicit is an assumption that the number of cross-sectional units, n, is large, as otherwise the asymptotics wouldn't really be relevant for the data at hand. So whenever you see an arrow and whenever we talk about asymptotics, they only really matter if you have a lot of cross-sectional units. All right, so today we'll take another look at the linear model for cross-sectional data, as well as the ordinary least squares, or OLS for short, estimator. This will serve in part as a refresher, reminding you guys of a lot of the stuff that you've seen in previous courses or your most recent econometrics course. But it'll also be a nice and gentle introduction to the use of asymptotics in your analysis. We'll be using asymptotics throughout this course, so it's nice to do it in a somewhat familiar playing ground. Also, the linear model and as well as ordinary least squares for cross-section will provide us with a useful benchmark for our later panel data lectures. Essentially, whenever in the next handful of lectures or so, when we start talking about panel data and estimators for panel data models, we'll try to come up with clever transformations which essentially bring us back to the cross-section in some sense. That will become much clearer, hopefully, later on. The outline for today's lecture goes as follows. We'll introduce or revisit the linear model for a cross-section, as well as talk about how we obtain identification of the parameters of the model. Then we'll talk about the OLS estimator and under what assumptions it can be shown to be consistent, and we'll actually go through the argument. Then we'll move on to talking about various components needed in order to do inference, and for that purpose we'll establish a result of asymptotic normality, and we'll talk about how to estimate the asymptotic variance or approximate the variance of the OLS estimator. And then I'll remind you guys of a tool called the Walt test, which is very useful for testing linear hypotheses. All right, diving into it, let's talk about the model and identification. So our interest here is in the following equation or population equation, stating that the outcome y is linear in regressors x, which here denotes a 1 by k vector, up to some unobservable term u. So u represents all the stuff that we've left out of the model, all the stuff that we cannot observe or cannot gather data on. Assuming that u given x, u has a conditional mean of 0, the model can also be expressed as the linear relationship also implies the following expression, stating that the conditional mean of y, given the regressors, is linear in x and therefore also in the parameters that we attach to x. Now, in order to identify the parameters from our linear equation up here, we actually only need the following two assumptions, OLS 1 and 2. The first states that the regressors are uncorrelated with the unobservable term u, and the second states that the expected outer product of the regressors has full rank. So this expected outer product here is a k by k matrix. So when we state that it has full rank, we're stating that it has a rank of k. Note here that we don't actually need that u has a conditional mean of 0 in order to identify the model. That is, that the conditional mean assumption implies this unconditional mean assumption. But it might be useful in order to endow the parameters of the model, the betas, with some sort of causal interpretation. Okay, so how would the argument for identification go? Well, if we go back to our linear equation, it looks something like this. And we pre-multiply by x transpose, which is a k by 1 vector. We get this. And calculating expectations on both sides of that equation, we arrive at the displayed equation. Now, under the first OLS assumption, which states that the unobservable term and the regressors are uncorrelated, the second or latter part of the right-hand side drops out, and we're left with this. Under the second OLS assumption, this expected outer product of the regressors matrix has full rank. Since it is a positive semi-definite matrix and it has full rank, it is also invertible, so we may actually solve for beta in our previous equation here and express it as the inverse of the expected outer product matrix times the expectation of x prime and y. Now note here that we've completely expressed beta as a function of two features or two components here. The expected outer product of the regressors and the expectation of x times y, or x prime times y. Both of those components are features of the joint distribution of y and x. So, in other words, if you were to give me the joint distribution of y and x, then I could calculate those two objects. Since we can express beta as solely features of the joint distribution of y and x, beta is identified, which just means that if you were to give me all the data in the world, then I could recover beta from the joint distribution of y and x. Moving on to talking about estimation and consistency. Alright, so now we're supposing that we have IID data stemming from our linear model. So we have n observations of y and x at our disposal. And these are independent and drawn from the same distribution. Now we're going to invoke a principle called the analogy principle, which will be useful throughout this course. Now, in case you haven't seen it before, the analogy principle states that whenever we encounter unknowns, we should aim to replace these unknowns with estimators thereof. That is generally a good idea. It's an even better idea if we can replace those unknowns with consistent estimators thereof. Now, since we've expressed beta as the product of two unknowns, it seems like a good idea to proceed as follows. Namely, replace expectations, whenever we encounter expectations, replace those with averages. That seems like a good idea from invoking the law of large numbers and the fact that we're assuming access to IID data. So we can directly go from our identification result and replace expectations with averages in order to arrive at the following. Beta hat is an estimator of beta, which arises immediately from our identification result when combined with the analogy principle. This beta hat is the OLS estimator, and here I'm expressing it in two different forms. One is the form arising directly from the analogy principle, that is, we're stating everything in terms of averages, which will be very handy later on when we talk about consistency, as well as when we talk about establishing some sort of asymptotic distribution of the OLS estimator. The second expression here is also very handy, but mainly for computation purposes. Here I'm stating or expressing the OLS estimator using solely linear algebra. And just to be clear here, this boldface capital X denotes the n by k matrix arising from stacking the xi's, which are all 1 by k. And this lowercase boldface y arises similarly from stacking the yi's, using the same order in both cases. So that's the OLS estimator, or one way of introducing the OLS estimator. Moving on to talking about consistency of the OLS estimator. Now recall that our distributions are assumed to be drawn from this linear model. So if we plug in those y's in the second expression here, or the second part of the product, and simplify terms, we arrive at this display equation, which states that the OLS estimator can be expressed as beta, the parameters that we're trying to estimate, plus the product of two terms. The first part of the product here is the inverse average outer product of the regressors, or regressor vectors, and the second is the average of the regressors when interacted with the unobservable UI. So the second part is not something we can construct from our data since it involves the UIs. This is unknown, but it's random. Now again, invoking our standing assumption of random sampling, or IID observations, and using the law of large numbers, we can show that the second part of the above product converges in probability to its expectation. What expectation? Well, it's the expectation of x prime times u, the unobservable. And under our assumption, OLS 1, this expectation is the zero vector. So here this both face 0 is k by 1. Now similarly, invoking random sampling and the law of large numbers, we can show that the average of the outer products of the regressive vectors converges in probability to the expectation of the outer product. Note here that the right-hand sides of these limits don't involve any i's or n's, since we're assuming that these observations are drawn from the same distribution. Hence, it's not really necessary to keep track of what distribution we're talking about, because they all come from the same. Now, what's important here is that the limit here, the limit matrix, again, this is k by k, is invertible by our second OLS assumption, OLS 2. Let me just pause for a second to say that when we're talking about convergence in probability for vectors as well as matrices, we mean convergence in probability element by element. So just to be clear, we're talking about the same notion of convergence in probability that you guys have encountered in the scalar case, or the usual random variable, single random variable case. We're just applying the notion element by element. All right. Having established this convergence in probability to the expected outer product of the regressive vectors, we can apply Slutsky's theorem, which you may encounter in Wooldridge chapter 3, to use that to argue that when the first part here converges in probability to E of x prime x, and the second also converges in probability, but now to the E of x prime y, or u, sorry, then they converge, the product also converges in probability to the product of their limits. Now here the rank assumption is important in order to ensure that the convergence in probability passes through this inversion part. If the limit matrix was not invertible, then the right-hand side would make no sense, and Slutsky's theorem wouldn't apply. So that's where the rank condition kicks in. Now, since the second part of the right-hand side limit is a zero vector, and the first part, well, exists, the product must also be a zero vector. And again, this is a k by 1 zero vector. So, to conclude, we've expressed the OLS estimator as beta, the parameters we're trying to estimate, plus something that vanishes in probability. Hence, the OLS estimator must converge to the parameters we're trying to estimate, namely beta. That is, under the assumptions OLS 1 and 2, the OLS estimator is consistent for beta. Alright, so we've established consistency of the OLS estimator, which is a neat result, but it doesn't really allow us to do any sort of inference. It doesn't facilitate inference. So let's move on to talking about a way for obtaining useful methods for inference. That is, let's move on to discussing the notion of asymptotic normality. For the purpose of establishing some sort of asymptotic normality result, we'll need the notion of convergence in distribution. So you may have seen this in your previous probability theory and statistics course, but just to be sure, we're going to go through it here. We're going to go through it here briefly in the vector case. So here's a definition. A sequence of g-dimensional random variables, which is just to say that we're dealing random vectors of length g. We say that a sequence of random vectors converges in distribution to a continuous random variable, here denoted by this capital boldface X, if for each candidate X, each lowercase boldface X, the following convergence hold. Namely, we can show that the CDF of this random variable xn, when evaluated at lowercase x, the CDF converges to the corresponding CDF of the limit, or rather limiting random variable capital X. So here this Fn denotes the CDF, or cumulative distribution function, of xn, and F without any n denotes the corresponding CDF of boldface capital X, which by assumption is a continuous function. That's what we mean by the random variable capital X, capital boldface X, being continuous. If we can establish that the sequence of xn's converges in distribution to a continuous random variable x, then we write that xn converges in distribution to x. Well, we write that convergence occurs in the d sense and write this arrow d. So here arrow d, or arrow with a d on top of it, denotes convergence in distribution. Now note here that Wooldridge, throughout the book, uses both this arrow D notation, but also this tilde A notation. He means the same thing, so you should think of this tilde A as being short for asymptotically distributed as whatever follows on the right-hand side. They're just two pieces of notation for the same concept. All right, so how would we go about establishing convergence in distribution? Well, in this class, throughout this class, we will primarily focus on arriving at convergence in distribution by means of a central limit theorem. Again, this may be a repetition to some of you guys, but here we're going to have to invoke a central limit theorem in a multivariate case, so I'm going to go through it slowly. Here I'm stating a theorem from Wooldridge chapter 3 again, which is a very nice background chapter that you may want to take a look at. The theorem states the following: if we're dealing with g-dimensional random vectors, or a sequence of g-dimensional random vectors which are identically distributed as well as independent, and also, this is the new part, they have zero mean, then their scaled average, this is square root n times their average, converges in distribution. And even better, it converges to a distribution, or a normal distribution with zero mean, so this here is a g by 1, 0, and having variance given by the expected outer product of these vectors w. Whoops, it's not k by k, that would be g by g in this case. All right, so why is the central limit theorem useful? Well, it states that even if the distribution of the wi's, even if that common distribution is unknown, then when we construct their average and scale it appropriately, here by square root n, then as n goes to infinity, we arrive at a normal distribution. That is, we recover a known distribution in the limit. Well, known up to this variance matrix. So whenever we're dealing with large samples, we could treat scaled averages of zero mean variables, zero mean and IID variables, as being approximately normal. Okay, let's go back to the OLS estimator and start thinking about establishing an asymptotic normality result. We already know that we can express the OLS estimator as the parameters we're trying to estimate plus something, being the product of, well, the inverse of an average and an average. Now, if we rearrange that previous expression, that is, we pull beta to the left-hand side and scale the result by square root n, then we get the following. We still have this inverse average outer product of the regressor vectors, but now we have a scaled average of the regressor vectors as well as the unobservables, the UIs. We've already established that the first part here, this inverse, converges in probability to the inverse of the corresponding expectation. So all that's left to do is to look at this second term. Now, invoking random sampling, giving us IID observations or IID data, plus a central limit theorem, and also using this first OLS assumption in order to ensure that the summons, the stuff that we're summing or averaging, ensure that they are all mean zero, we can invoke the central limit theorem to show that this second scaled average converges in distribution to a normal with mean zero. This should be a vector of length k. And the variance here is now the expectation of u squared x prime x, which just arises from taking our summits and using the fact that the u is scalar to put it really anywhere, so why not in front, such that we get u squared and x prime x inside the expectation. All right. So in large samples, this second part is roughly normal. And to be specific, it is asymptotically normal. All right. So we've established two separate convergence results, one for the inverse average outer product matrix, and one for the scaled average of x primes and ui's. Now, how would we combine these results? For that, we need the following result. So here's a neat result giving us a way of combining different modes of convergence. And we'll refer to this rule or result as the product rule. So the rule goes as follows. If we have the following two conditions satisfied, that is, if we have a sequence of random variables, these could be vector, these could be matrix, and they converge in probability to a constant vector or a matrix, and also we have a sequence of random variables, these could be vector or matrix, which converge in distribution to some limit we'll denote here as a capital set. Then the following holds. The product of these two sequences, yn and zn, or zn, converges to the product of their respective limits, which is c and z. And in what sense? Well, in distribution. So even though these two convergences are in different senses, we can combine them to get a mode of convergence for their product. Now, I want to stress that constancy of the limit of the YNs, that is, constancy of this possibly matrix C, cannot be disposed of. That is, if the limit of the YNs is random, if the probability limit is random, then this latter convergence need not hold. So be careful when applying this rule. However, this rule will hold in our case, and we'll use this product rule again and again. Now, before I invoke this rule, I just want to stress that when I'm talking about applying this rule, or talking about establishing this type of result, I'm implicitly assuming that the YNs and CNs, or ZNs, are conformable. That is, they have their dimensions match in order for me to construct their product in a meaningful sense. All right, let's move on to applying this rule. Now, we've already established that this inverse outer product, or average of outer products, converges in probability to the inverse of the expected outer product, and that this scaled average converges in distribution to a mean zero normal with variance given by this expression. Oops. All right, now the product rule allows us to conclude that since the limit of the first part is constant, right? This here is a constant matrix, then we can conclude that the product of the two converges in distribution. And the limit is given by this inverse expected outer product playing the role of C in the product rule, and this normally distributed random variable playing the role of set in the product rule. All right, that's neat. But there's actually a way of further reducing the previously displayed limit random variable and express it in a more convenient manner. For that, we'll use a property, which is rather unique in that it's a property of the family of normal random variables. The property goes as follows, that is, if C is a constant matrix, or C is a constant, possibly matrix, and set is normally distributed with mean zero and variance given by some variance matrix, let's call it V, then C times set is distributed with zero mean, variance given by CV C prime, but more importantly, it is also normally distributed. That is to say that if we take a linear transformation of a normal random variable, then we get a normal random variable back. More generally, this result applies to any affine transformation, and sometimes you'll see this result expressed as the normal random, or the normal family being closed under affine transformations. This is also a very handy result, or very handy property of the normal family that we'll invoke again, and in fact later this lecture. All right, so what have we done? All in all, we've shown the following. As the sample size goes to infinity, or grows without bound, the difference between the OLS estimator and the parameters that we're trying to estimate, when scaled by square root n, this difference converges in distribution to a mean zero, normal, with variance given by a sandwich formula. And here the meat in this, or rather the bread in this sandwich formula, so this is the sandwich that I'm talking about. The bread is the inverse of our expected outer product matrix, or expected outer product of the regressors matrix, which we'll denote by A. The meat of the sandwich we'll denote by B, and it's the variance from the second part of our product, which is the expectation of the unobservable squared times the outer product of the regressor vectors. Now, often, when we establish a result like this, we'll say that the estimator in question, or the estimator under the loop, is square root n asymptotically normal, or just for short, asymptotically normal. So what we've shown here is that under assumptions OLS 1 and 2, the OLS estimator is asymptotically normal. And we've expressed the variance of its distributional limit, that is, the variance of the right-hand side up here. Right. Having established asymptotic normality of the OLS estimator, let's move on to talking about how we would estimate the variance of the OLS estimator. Now, as I mentioned in the introduction, this asymptotic result, stating that the centered and scaled OLS estimator converges in distribution, is not interesting in itself. It's interesting because it allows us to do the following approximation. Namely, if we treat, in our previous result, if we treat this convergence in distribution as a equality in distribution, or often written as just a tilde, an exact distribution, then we can again use that we can divide on both sides by square root n and move beta to the right hand side in order to arrive at the following approximation, stating that the OLS estimator itself is approximately normally distributed with mean beta and variance given by a previous sandwich divided by n. Divided since we've pulled the square root n, or 1 over square root n, inside the variance term. Now this is a bit of a heuristic argument. I'm being somewhat loose here. And this notation double tilde d reads only as approximately distributed as, which is just a useful shorthand, but admittedly somewhat loose notation for approximate distributions. However, this idea of approximating the OLS estimator by something that's normal should be a pretty good approximation in large samples, since we've established an exact normality result in the limit. All right, moving on to talking about how we would estimate let's move on to talk about how we would estimate the asymptotic variance. Now, this may be a potential source of confusion, so let me try to preempt some questions here. Now, our previous limit result shows that square root n times the difference between the OLS estimator and the parameters we're trying to estimate converges in distribution to a normal with variance of this sandwich form, right? So in particular, if we look at the variance of the stuff on the left-hand side, if we look at the variance of this stuff, then we've shown as a byproduct that the variance in the limit is given by the limiting variance. That is, the variance of this square root n term converges as the sample size grows. It converges to the sandwich expression on the right hand side. So let's just give that a name. Let's call it V henceforth, denoting variance. Then V is, strictly speaking, V is the asymptotic variance of square root n beta hat minus beta, right? It is the variance that arises in the limit, hence being the asymptotic variance. Nonetheless, given this idea on the previous slide of using an asymptotic normality result to obtain an approximate normality result, we may introduce the following concept. Namely, if we divide both sides by n, or square root n, and move beta to the right hand side, then our approximate normality result shows that the asymptotic variance of the OLS estimator, well, maybe we should call it the approximate variance of the OLS estimator, is V over n. Now we'll follow Woolchurch here and denote this as the asymptotic variance of the OLS estimator. This may be a bit confusing because given our result of consistency of the OLS estimator, we know that in the limit, the OLS estimator collapses to beta, which is non-stochastic, hence has zero variance. So a better name for the asymptotic variance of the OLS estimator, the notation we just introduced, would be the approximate variance as suggested by our asymptotic normality result. But life is simply just too short to say that every time we need to talk about it. Hence the reason we've introduced this useful shorthand notation and simply reduced the previous expression to the asymptotic variance. Now, this shorthand means that allows us to make statements such as V hat over n consistently estimates the asymptotic variance of the OLS estimator, or just beta hat when we're talking about a potentially different estimator. When we say that stuff, taken literally, it doesn't make much sense. So you should interpret it as the V hat being consistent for the V matrix. Again, this is a somewhat imprecise shorthand, but it's going to be very convenient. And since Woolchurch does it throughout the book, it doesn't make much sense to try to introduce a different notation, or at least I think it would just cause more confusion. So let's stick with this AVAR, or asymptotic variance, notation. All right. Now, how would we go about estimating the asymptotic variance of the OLS estimator, as understood on the previous slide? Well, we know that it is, strictly speaking, A inverse B A inverse divided by n. Now, we don't know A, we don't know B, so we can invoke the analogy principle and simply replace these quantities with consistent estimators. And here, the consistent estimators that I've chosen is going to be arising directly from the analogy principle again, where I've replaced the expectation, the expected outer product of the regressive vectors, by the average. At least for A, that is a pretty straightforward, or that's an estimator which is somewhat straightforward to justify. When it comes to the meat in the sandwich formula, or the B matrix, our estimator is slightly more complicated. We first replaced expectations with averages, that would yield us the average of the ui squares multiplied by the outer product of the regressive vectors. But it wouldn't be known since we don't actually observe the ui's. However, we can estimate the ui's using the OLS residuals and substitute them or plug them in whenever the ui appears, which is inside the square. So the B estimator arises from two steps. One is a straightforward application of the law of large numbers, or one is suggested by the law of large numbers, and the other takes a bit more thought, but it's something that shouldn't be too foreign given your econometrics training from the previous course. I just realized that there's a slight typo here. There should be no transpose. All right, so with these components of the asymptotic variance being estimated, we can estimate the entire asymptotic variance v hat over n by plugging them in correspondingly. And what we arrive at is this top expression up here, where we've canceled out any redundant n's, right? So all the divisions and multiplications by n that pop up end up canceling each other out, and the asymptotic variance estimator here simplifies. So that is our asymptotic variance estimator. Note here that this estimator can be shown to be consistent without any further assumptions, specifically without any assumptions regarding heteroscedasticity of the unobservable terms. So in that sense, it is robust to heteroscedasticity. However, if we are willing to make a heteroscedasticity assumption, or rather a homoscedasticity-like assumption, we can show the following. So let's just, for the moment, let's introduce another assumption. Let's call it OLS3, which states the following. It says that the expected value of the squared u's times the outer product of the regressors can be written as some constant, sigma. This is just a constant. And in fact, a scalar times the expected outer product of the regressors. In other words, what we called B is proportional to A with proportionality factor given by whatever this constant sigma square is. Now, under this additional assumption, OLS3, one may show that the OLS estimator is efficient. Efficient in what sense, you may ask? Well, it is efficient in an asymptotic sense. That is, it obtains the smallest variance asymptotically among the estimators possible. Now, whenever we talk about efficiency henceforth, we are talking about efficiency in an asymptotic sense, since we won't be relying on any finite sample results. I won't go through the argument here, since it completely mimics the result from your previous class, or rather the proof of the Gauss-Markov result. Now, with this additional assumption in play, this OLS3 assumption, we can exploit the additional structure to show that the asymptotic variance or maybe divided by n simplifies to sigma squared A inverse over n. Hence it has this neat product form where we only need to estimate sigma square and A. We've already constructed an estimator of A, which we can use again. So all we need to do is to estimate sigma square. And hopefully this formula will not be too foreign to you guys. We'll estimate sigma square by the average of the squared residuals. Well, with this slight modification that we've introduced a degrees of freedom correction, or adjustment, if you will. Adjusting for the fact that we've already estimated the k parameter coefficients. The k coefficients, the k betas. Now, of course, this variance estimator is only consistent under the assumption OLS 3. If, in other words, if OLS 3 is violated, the variance estimator need not be consistent, and we should rely on a more robust version for inference, that is, the variance matrix on our previous slide in purple. Also, if OLS 3 is violated, the OLS estimator is not necessarily asymptotically efficient. That is, we might be able to do better in terms of having a smaller limiting variance. Now, having established methods for obtaining an asymptotic normality result, as well as a way of estimating the resulting asymptotic variance of the OLS estimator, let's talk about how you would use this type of result in order to test various hypotheses. Here we're going to focus on testing linear hypotheses. So, by that I mean we're going to be interested in testing hypotheses of the following form. So here H0 denotes the null hypothesis. And the hypothesis can be expressed as the following restriction, saying that some hypothesis matrix, boldface R, times the underlying parameters beta is equal to some hypothesis vector, let's call it boldface lowercase r. Now, strictly speaking, this matrix R should have rank equal to Q, the number of restrictions that we're trying to test, which cannot exceed the number of parameters in the model. That will become more clear later on. Now, if we're interested in testing this type of linear hypothesis, then how would we go about it? Well, we know that the OLS estimator, at least under our previous assumptions, OLS 1 and 2, the OLS estimator converges in probability to beta. So it's not too far-fetched that it should be close to beta. Well, in that case, or at least it should be close with high probability. In that case, if we multiply it by some matrix, capital R, then the product of that R and the OLS estimator should be close to the product of R and beta. Well, under the null hypothesis, that's just lowercase r. So in other words, r beta hat minus lowercase r should be small, or close to 0, if you will. Now, a way to formalize this idea is to take the difference between r beta hat and lowercase r and divide by their variance, or rather divide by their standard deviation. Well, here we're dealing with vectors, so in order to carry out this division, we're going to compute this quadratic form, which is again a sandwich of the difference that we hypothesize should be small with high probability, at least for the true betas, it should be 0, And when we put that relative to the variance, to this variance term, it should be small as well. Now one may show, or rather, this sandwich formula, this quadratic form, is known as a Wald statistic, hence the W notation. And one may show that under the null hypothesis, that is the set of linear hypotheses from above, as well as our previous OLS 1 and 2 assumptions, the Wald statistic converges in distribution to a chi-square distributed random variable with q degrees of freedom. So q here again is the number of restrictions that we're trying to test. All right, with this convergence in distribution result suggests the following testing procedure, which is to say that pick a significance level, say alpha, this is some number between 0 and 1. Then we should reject the null hypothesis at this significance level if and only if our Wald statistic exceeds the 1 minus alpha quantile of the chi-square distribution with q degrees of freedom. That is graphing the PDF of a chi-square with q degrees of freedom. We should find the number, say critical value C alpha, that leaves alpha in the right tail. And we should reject the null hypothesis if the Wald statistic exceeds that number. Now the Wald statistic here can be made robust to heteroscedasticity if the robust variance matrix for the OLS estimator is used. Also, this idea of Wald testing is not limited to the linear model in the cross-section and to using the OLS estimator. It also applies to our later lectures when we'll talk about panel data as well as various estimators for the panel data model. All right, let's spend a moment just thinking about why the Wald statistic takes its form again. Here's another neat fact about normal random variables. If Z is a normally distributed random vector of dimension g, or length g, it has 0 mean and some variance matrix, let's call it capital sigma. Then if we construct the quadratic form with the inverse variance matrix, the inverse of sigma, in the middle, and sandwich it by the vector set in order to construct a random variable, then that random variable is chi-square distributed with g degrees of freedom. Again, g being the length of the random vector z. Now, this type of property or result is really just a multivariate version or analog of the fact that if we take a 0 mean normally distributed random variable, divide by its standard deviation, and square the result, then we get a chi-square distribution with 1 degree of freedom. Here, since C is g-dimensional, the division part goes through multiplication by the inverse variance matrix, and the resulting chi-square random variable has g degrees of freedom. But that's the only difference, really. Now, our previous normal approximation result can also be used to show that, or used to argue that the difference between the OLS estimator and the parameters we're trying to estimate is roughly normally distributed with 0 mean and variance given by this v over n. So if we treat this approximate distribution as an equality and apply the linear transform given by our testing matrix capital R, then the resulting difference should be roughly normally distributed, again with 0 mean, now being of dimension q, since R has q rows, and variance given by R times the original matrix, V over N, times R prime. Again, we're using here the property of the normal family, which shows that the normal family is closed under linear transformations. Now, if we go back to the above fact relating the normal family to chi-squares, and we construct this quadratic form, substituting our current z for this difference in products, and our current sigma, then we get that the difference between r beta hat and r beta, or the sandwich created from r beta hat minus r beta, and rv over n, r prime, inverted, should be roughly chi-square distributed with q degrees of freedom. Now, under the null hypothesis, r beta is just equal to r, and since we don't know the asymptotic variance of the OLS estimator, we'll use the analogy principle to replace it by a consistent estimator, which could be of the robust form if we're not willing to make a homoscedasticity assumption, or it could be of the non-robust form if we are. But that explains why the Wald statistic takes the particular form on the previous slide. Alright, so what type of hypotheses may we entertain in this linear hypothesis world? Well, one example could be to test the hypothesis that the coefficient on x1 and x2, that is beta 1 and beta 2, are in fact the same. Well, that's just one restriction, so the R matrix is just a single row vector, and it's given, and we can rewrite the hypothesis of equal coefficients as an hypothesis of their difference being 0, such that all we need to do is use an R matrix of 1, minus 1, and 0, and a right-hand side of the scalar 0, since we only have one restriction. A similar type of hypothesis states that the sum of the two coefficients, beta 1 and beta 2, is equal to 1, which is very similar to the previous example, except that we now use an R of 1, 1, 0, or capital R of 1, 1, 0, and a right-hand side of 1. A slightly more complicated example, or slightly more involved hypothesis, is the equality of all three coefficients. Now note here that since we're claiming equality between beta 1 and beta 2, as well as beta 2 and beta 3, we really have two hypotheses that are being tested. But in order to get that in a format suitable for Wald testing, we can write again the first restriction as beta 1 minus beta 2 being 0, and the second restriction as beta 2 minus beta 3 being 0. In matrix form, it yields an R of 1, minus 1, and 0, and 0, 1, minus 1. And again, the right-hand side is a big fat 0, except that there are now two of them, since we're dealing with two restrictions. A word of caution here. You may ask, what about the restriction that beta 1 is equal to beta 3? Well, it's already implied by the two previous restrictions, so we shouldn't include it in our R matrix. And in fact, including it in our R matrix would lead to a violation of our previous restriction on the R matrix that it has full rank. I'll leave that for you guys to show on your own. All right. The last type of hypothesis that I'm going to list an example of here is that, well, all of the coefficients, beta 1, 2, and 3, are in fact 0, which is to say that none of the variables attached to these coefficients actually matter in our model. In that case, we can just choose an R equal to the identity matrix here in 3 dimensions, and a right-hand side of a big fat 0 again, except that we have 3 zeros. All right, that concludes today's lecture. Next time, we'll start talking about panel data as well as various methods for estimating the linear panel model.